So now we're going to look at how the atomic mass or the atomic weight of an element is calculated. If we look at neon in the periodic table, you'll see the symbol for neon. There it is, Ne. And then the number above it, the number 10, is Z, which is the atomic number. So that defines the number of protons and therefore also defines the number of electrons in any given atom of neon. The number below it is called the average atomic mass, and the units are atomic mass units. Now, if we look at a sample of neon, it has three different isotopes. The one that is the most plentiful is neon 20. So neon 20, all of these atoms have 10 protons, right? And then 20 neutrons. The next one that's the most abundant is neon 22. So roughly, out of neon 20, roughly 90 out of 100, right? 90.48% is neon 20. If we look at neon 22, roughly 9 out of 100 will be neon 22. So that's 10 protons and 12 neutrons. And then neon 21, less than 1 out of 100 is going to be neon 21 with 10 protons and 11 neutrons. Now, the way you calculate the average mass for these elements, these are not weighted equally because they're not equally populated. They're not in equal abundance. So the way we're going to calculate this is what's called a mass weighted average. So each one is going to be weighted by how often it appears in the sample. Before we show you how to calculate that, let's talk about an average that you're used to calculating. In this case, the different components are weighted equally. Imagine that you took 3 chemistry tests and you worked hard enough that you got 100 on the first one, a 95 on the second one, and a 92 on the third one. When you calculate your average of the 3 tests, you add up your 3 test scores, and then you divide by 3 and you get the average 95.7. Now, what's actually happening here, you can look at it this way, but the other way you can look at is that the weighting factor of each exam is the same. It's 1/3 each. In other words, we could rewrite this as 100 times 1/3 plus 95 times 1/3 plus 92 times 1/3, and we have the same thing, right? So the 1/3 is equal for all of them. We're treating each test equally. Now, what if the instructor of the chemistry test finds that he doesn't think that the test should be weighted equally because the number of questions is different? Let's say we have 10 questions for the first test, 10 questions on the second test, and 20 questions on the third test. Well, the instructor might think, well, I don't want to weight these equally. I want to weight them on the basis of how many questions there are in the test. Well, then the weighting factor you would have to calculate for each one. We could rewrite this. The average would be calculated this way. We need a weighting factor. It's 10 questions for the first test divided by the total number of questions, which is 40. And that becomes 1/4, or 1/4 times 100. Plus the second test has 10 questions. So the weighting factor again is 10/40 times the grade for the second test. And now the third test has 20 questions out of 40. And we multiply by 92. So again, this is called a weighting factor. Here the weighting factor is 1/3 treated equally. Here the weighting factor is 1/4 or 1/4. 1/4, and this is 20/40 is 1/2. So again, this part is the fractional amount. If we go back and look at what we were talking about here, this is what we're referring to. So the first weighting factor was 10 questions out of a total number of 40 questions. So I hope you understand that now. let's look at how we can use these weighting factors to look at a mass-weighted average. Well, now, the way we would calculate the average atomic mass here is take the mass, say, of neon 20, and multiply by something called its fractional abundance. Well, what is that? Well, it's how often you find it in the sample. This is its fractional abundance, 90.48%. But to make it look like this, a fraction of 1, we need to divide by 100 to remove the percentage factor. In other words, what we want, if we have our percent here already, right? Like in this case, we had 3 divided by 100 times 100 is 3%. We're talking about now taking the percentage value at 3%, divide by 3, and you get 0.03, a fraction of 1. So that's what we need to do for our weighting factors, just like we did here. So let's show you how to do that on the next slide. So here is the actual data for the masses of neon 20, 21, and 22. Now note that the mass is not exactly 20, 21, or 22. This is the actual mass. These are measured in a special instrument called a mass spectrometer. Those are details that you don't need to know anything about. Look at how many significant figures we have. That's because a mass spectrometer is very precise. In addition, you get how often you see the different isotopes in a given sample. So to do the calculation now, we take the mass of the first isotope, neon 20, we put its mass there, and then we multiply it by its fractional abundance, okay, which is 90.48%. We remove the percent by dividing by 100. That moves the decimal point there, and we have 0.9048. We now add that to the contribution from the next isotope, neon 21. This is that mass multiplied by its fractional abundance. So this is again percent, so we remove the percent by moving the decimal point over to the left, 2 spaces. And then we just do the same thing for the third one, right? There's the mass. Convert this to 0.0925. So you get out your calculator, you multiply these, you add it to the result of this, and add it to the result of that. Now, we need to keep track of significant figures here, and the multiplication rule of these two, this is 4 significant figures, and it's smaller than that. So when we get this value, we don't round yet, but we identify that if we were to round, we would round at the 4th significant figure. Here, we only have 2 significant figures, so this limits this value to 2 significant figures there. And then finally, this one, we have 3 significant figures here. Again, we have 6, so this limits how many significant figures we need to report in our final answer here. But again, we don't round yet. Okay, we just identify where the uncertainty is. Now we apply the addition-subtraction rule. The uncertainty here is in the hundredths place, thousandths place, hundredths place, so we need to report our final answer to the hundredths place. So we underline here, and now we're ready to complete our rounding, right? So the number after the 8 is 4 or less, so we round to 20.18. Atomic mass units. Now, if you go look in the periodic table, this is the number you're going to see. And now to round up our discussion of isotopes, I have 2 slides dealing with applications of isotopes in medicine. So you're not going to be responsible for knowing any of this on the test, but I thought I would just bring this up so that you can see a relevant application of isotopes and see how important they are. So first of all, the PET scan stands for positron emission tomography. So a positron is the antiparticle to the electron. So the electron has a certain mass and a negative charge. The antimatter particle, called a positron, has the same properties of the electron. It has the same mass and the same charge, but opposite in sign. That's the only thing that's different. It's a positively charged electron. Now, whenever a matter particle collides with its antimatter particle counterpart. In this case, whenever an electron collides with a positron, the matter disappears. They both annihilate, and what you create are two packets of light called photons. They move in opposite directions. They happen to be gamma rays, and they can be detected really in almost 360 degrees around here. So you're able to detect where the positrons are formed as they're coming out, right, forming the gamma rays, and from where it hits on this detector, you're able to deduce exactly the origin of where it came from. So it's useful in this case for diagnostic imaging. So if you take the isotope carbon-11, which does not exist in nature, you have to make this in a device called a cyclotron. It has a very short half-life. So a half-life of 20 minutes means half of the sample disappears or decays in 20 minutes. So it's pretty much all gone after 5 half-lives, or about 100 minutes. So a radiochemist makes carbon-11 in a cyclotron and then very quickly has to do some chemistry to make the molecule glucose with it and then inject the patient with glucose. Now, the only type of molecule that neurons in the brain can use for energy is glucose. That is it. Nothing else will work. So it's helpful in the sense that if you label glucose with carbon-11, the glucose makes its way to the brain, and then what you're imaging here is brain activity, right? Highly functioning neurons are going to be consuming a lot of glucose, so you're going to see concentration of the glucose in those regions. This is a false color image of a normal brain that's functioning. And we can see here is the brain of an Alzheimer's patient. So you can see the blue and black. Blue means very little activity, black means pretty much none. So you can see that there's quite a bit of the brain here that's not working very well, presumably because amyloid plaques have formed. So in addition to diagnostic imaging, radioisotopes can actually be used for therapy. So the one I'm going to talk to you about here is called Neutron Capture Therapy. So this is a promising type of therapy for solid brain tumors, which really can't be treated by anything else. The way this works is, again, a radiochemist takes boron-10 and puts it into a molecule that's designed to accumulate in neural cells of tumors. So one thing that's distinctive about tumor cells and normal cells is that tumor cells are metabolically a lot more active. They require much greater blood supply, and so boron-10 in a particular molecule will accumulate specifically in the tumor more than healthy tissue around it. Then the special property of boron-10 is that when a neutron beam bombards the boron-10 nucleus, it splits. It splits into lithium-7 and an alpha particle. Now, an alpha particle is just a helium nucleus with a 2+ charge. And the alpha particle is very energetic. It moves fairly slowly, but it's like a wrecking ball. Wherever it's formed, it's going to do damage. And the point is, if you irradiate the tumor that has accumulated boron-10 with a neutron beam, then you're creating damage directly in the tumor and nowhere else. So it's a very promising therapy for taking out solid brain tumors. It's kind of interesting to find out why it hasn't really caught on. And I don't really know that answer, but it's kind of surprising. It could be that there's no good neutron sources in hospitals. I'm not really sure why, but I would think that this is a very promising therapy for taking care of brain tumors. All right, so that ends our section here on isotopes.